Hi, welcome to Lecture 3. This is all about beginning of calculus, about change and an introduction to limits. So we'll start by talking about some general things about the word change and what calculus is all about really. The best definition of calculus, at least the first part of calculus, what we call differential calculus, maybe the best definition of that is the study of change. So anything that changes, we study, or we can study, with calculus. And to begin that, let me say that change is not the easiest thing in the world for people to understand at first, because it's different from anything else that you've ever really tried to think of. And I have a good example of that. Suppose that we talk about somebody's salary, and somebody comes up to you and they tell you that their salary went from $10,000 a year all the way up to $100,000 a year. Impressed? Well, maybe. Suppose that they then told you they started at $10,000 a year 50 years ago, and just this year they managed to make it up to $100,000. So it took them 50 years to get their salary to go from $10,000 to $100,000 a year. The thing is, that's not so impressive. To understand the change in salary, it's not enough to know that the salary went up by a lot. You also have to know something about how long it took to get from 10,000 to 100,000. That's a big change, but if it takes a long time, it's not as impressive, if it took 50 years as if it took, let's say, 5 years. Somebody who could go from 10,000 to 100,000 a year in 5 years, that's pretty impressive. So there's something about both of these things, that is, the change in the amount of the salary and the change in the amount of time that is required to understand change. So you can't understand change if you only hold one number in your head at once. That is the difference in the salary. You also have to know how long it took. So in fact, to understand change, there's two quantities. There's a difference, like an A minus B in the salary, and then there's a difference in times, so like P minus Q. And you end up dividing the two to form a ratio. And it's that ratio that measures the change. Another example that is very familiar to you, and is probably what you might have expected as the first example, is to talk about speed. Speed is described, at least in physics, as change in position. So let's say you got in your car and you drove from Valparaiso to Merrillville. A distance of, maybe 15 miles. Okay, then the change in distance is 15 miles. That doesn't tell you anything about speed, but speed is the change in distance with respect to time. So you have to have both distance and time in your head at once. So if I told you that I traveled from Valparaiso to Merrillville, a distance of 15 miles, and it took me 30 minutes, which is the same as half an hour, then I would divide the 15 miles by half hours, and I'd end up with 15 divided by a half, which you can flip the bottom and multiply by it, so you get 15 times 2 miles per hour. And 15 times 2, of course, is 30. So 30 miles an hour is how fast you were traveling. Now, of course, what this is commonly called is the average speed. And we won't be talking all the time about speed. We'll certainly talk about speed a lot, but average rate of change is the quantity that we're really talking about here. And always, the average rate of change is going to be this kind of ratio. It's going to be the change in one quantity divided by the change in another. The bottom part will often be time, like this, but not always. We'll see lots of examples where it isn't. And the top quantity will be who knows what. Sometimes it's money, sometimes it's distance, sometimes it's things that are very abstract. In any case, the change in one quantity relative to the change in the other quantity is what we call this average rate of change. And we have a special notation for talking about that. Let's say, for example, that we were talking about cost. And there's a change in cost associated with doing things. And maybe time is the other quantity that we want to keep track of. And so there's a change in time. And so the cost will change over time. So if we wanted to talk about the average rate of change, then we would calculate the difference in cost divided by the difference in time. And as you know, in math, we usually abbreviate things tremendously. So we might use the letter C for cost and T for time. And then the average rate of change would be written this way: delta C divided by delta T. And this would be read the average rate of change of the cost relative to time. All right? If we did position, if we measure position as x, x equals the position of something, and t would be equal to the time, then we use our delta notation and we write delta x divided by delta t, and this would be the average change in position with respect to time, or the average rate of change, or the average speed in this case, because speed is change in position with respect to time. This triangle that I've been using, I'm calling it delta, is a Greek letter. We borrow it from the Greek alphabet, and it's capital delta, which corresponds to our letter D. And a lot of the fraternities and sororities use delta in their names, but this is the capital letter delta. And whenever you see that in mathematics, you've got to think change. So this is the change in x with respect to the change in t, or the average rate of change, the average speed. Okay? Now that's where we start with studying change. But of course, if you look at our example with driving to Merrillville, we went to Merrillville, a distance of 15 miles, and it took us half an hour, and so we're saying that we traveled 15 times 2, 30 miles per hour. But of course, if you have ever actually driven from Valparaiso to Merrillville, 30 miles an hour is very rare. You're not traveling 30 miles an hour, at least not very often. You're either traveling 55 or 60 on Highway 30, or you're moving not at all because you're stopped at one of the 4,000 red lights between Valparaiso and Merrillville. And in that case, you're not traveling at all. But on the average comes out to be 30, even though you're not traveling 30 very much of the time. So this idea of an average might be useful for some purposes, but there's another idea that we want to get to, which gets us a lot of mileage. It gets us a lot of information that we don't have if we just study the average rate of change. We want to get to the idea of what's called the instantaneous rate of change. And this idea gets at how fast are you really going at a particular instant, or focusing on a particular point and trying to measure change at a point, which sounds like it's absolutely absurd, right? How can you have change when you're looking at one instant in time? And that used to be one of the philosophical problems that baffled the Greeks, and they loved to argue about this late into the night. How can you have change at a point? Nothing can ever happen at one point in time, so there is no change. Well, that was one of the Zeno paradoxes. Well, with calculus, we can actually explain that, because what we are really talking about is not exactly the change at a point, which of course would be meaningless, but what happens to this average change in whatever, let's say x, with respect to some variable t. What happens to this average rate of change if we think about the change in time getting smaller and smaller and smaller? We say going to 0. Well, that's a difficult question. You can't just answer it just looking at this. You have to know the data. You have to look at what's going on. And so we'll see lots of examples where we'll have relationships that tell us what x is as a function of time, and then we'll be able to calculate that change over time and see if we can tell what's happening as the change in time gets closer and closer to zero. And there are plenty of cases where we can tell exactly what's going on, and it's what you might think. Other times, it's not clear at all what's going to happen. Now, it sounds like I'm waving my hands here, but there are tons of examples that we can look at. But right now, I think that rather than talk about examples, it's really a good idea to focus on what the big picture is, and we'll dive into the examples in a few more minutes. The big picture is that we are still here talking about the average rate of change. But when we make the change in time get smaller and smaller and smaller, then this ratio changes and does what? Well, sometimes this ratio gets closer and closer to some particular value. And this particular value, whatever it might be, is going to be what we call the limit of the average rate of change. So we might say that this average rate of change, delta x over delta t, gets closer and closer to some limit as delta t gets closer and closer to zero. Or to put this in more English terms, as the change in time gets smaller and smaller, this average rate of change might get closer and closer to some number. Okay, let's look at a couple of examples, one of them fairly easy, where we just simplify what we're looking at. Instead of this looking at explicit delta x's and delta t's, let's suppose that what's in the parentheses there just turns out to be something like t squared minus 1 over t minus 1. And so the question is, what happens to this thing as the change in t goes to 0? Well, the change in t in this problem is this t minus 1. So t minus 1 is going to 0. So this really means that t is getting closer and closer to 1. All right, so if t is getting closer and closer to 1, t minus 1 is getting closer and closer to 0. The bottom part is getting closer and closer to 0. And normally when we have a fraction and the bottom part gets closer and closer to 0, think of that. Think about that. You have a fraction, just let's not even use x, let's just use 4. If you divide 4 by a number that's getting closer and closer to 0, then that makes this fraction get bigger and bigger and bigger and bigger. So normally when you divide by something that's getting small, you expect the fraction to get big. But notice that if t is getting close to 1, t squared minus 1 is also getting close to 0. So what we say is that the bottom is getting close to 0 and the top is getting close to 0. And this, folks, is what we call bad news. It's bad news because you cannot tell just from looking at this what happens. Remember this from now on. We'll do this a million times, not just in Calc 1, but you'll see it again in Calc 2 and Calc 3 and throughout the rest of your life. When both the numerator and denominator get close to 0, you cannot tell what's going on. If you make a conclusion at this point, it's wrong. You cannot tell because 0 over 0 could be anything. There are instances where 0 over 0 gets close to 17. There are instances where 0 over 0 gets close to 0. There are instances where 0 over 0 blows up, gets bigger and bigger than anything. And there are instances where 0 over 0 doesn't get close to anything at all. It just has no limit at all. So there is no conclusion that you can draw. It doesn't mean that you're done. Quite the contrary, it's bad news because it means you have a lot more work to do. In this particular problem, it's not very difficult because the question is what happens as t gets close to 1, not what happens when t equals 1. When t equals 1, this is stupid. The denominator is 0 and you don't know what happens at 0. It's like the Greeks would have said, there's no change at the point when delta t is 0. There's no change there. Well, that's not what we're talking about when t equals 1. We're talking about what happens when t gets close to 1. So we have to look at this differently from the way that we looked at in algebra, or at least analyze it. We'll do a little bit of the work just like we did in algebra though, because most of you are probably thinking, well, can't I just rewrite t squared minus 1 over t minus 1 as t minus 1, t plus 1, factor the numerator, divided by t minus 1? And the answer is yes, you can. And as long as t is not equal to 1, then you can cancel these parts here, leaving you with t plus 1. Now, let me pause here for a minute because this relates to what we were talking about just the other day. If you're looking at this function right now as a function, what's the domain? The answer is, the domain is any t that's not equal to 1, because you can't plug 1 into this because it'll give you 0 in the denominator. What's the domain of this? The answer is all real numbers. So technically speaking, this function is not equal to that function, except it is as long as you allow for t not to be 1. As long as you require t to be anything but 1, then these two are different functions. So what's the point? If the question is what happens as t gets close to 1, then you don't really care what happens when t equals 1. You care about what happens as t gets close to 1. So that means t is not going to be equal to 1, just close. As close as you want to get. So that means then that this function is okay everywhere because we're not going to allow t to be equal to 1. And that means that this function and this function, t plus 1, are the same function. Because I'm making this restriction. T is not allowed to be equal to 1. Alright, so the final analysis question is, what happens now? If this was what we were analyzing, and this behaves just like t plus 1, I can tell what happens to this function as t gets close to 1. And that's child's play. As t gets close to 1, it's obvious that t plus 1 is getting close to 2. If t is getting closer and closer to 1, then t plus 1 is getting closer and closer to 2. Now, for some people who are math majors and who go into a theoretical analysis of math, we end up having to prove obvious things like this. But for most of the rest of us, we can certainly buy that as t gets close to 1, t plus 1 is getting close to 2. But don't make that mistake up here with this fraction. It's not obvious at all, just glancing at this, what's happening as t gets close to 1, as t approaches 1. And from what we just did now, we can tell that the answer is that this whole fraction behaves just like t plus 1, which is going to get close to 2 as t gets close to 1. So this fraction got close to 2. Now we're going to look at a lot of examples of this in the lab, and it'll make much more sense. But for now, we're just doing a little bit of analysis without doing any pictures, without plugging in any data. I would like you to take a look at the examples that are done in the book. They do a nice job right here. Take some time to actually look at them, particularly examples on page 87, 88, 89. And there's one example in particular that's very, very wonderful. Fantastic example on page 89. I want to summarize it here. And they do something that's very interesting and kind of important for us. So let's just talk about that example. This is from page 89. You can look at it yourself when you take out your book. On page 89 you have this example. What happens to this function, the square root of t squared plus 9 minus 3, all divided by t squared? What happens to that function as t gets close to 0? Right? That's the question. What happens to this complicated function? Again, this is one of those nasty situations where obviously t squared is getting close to 0 as t gets close to 0. The bottom is getting close to 0, but then so is the top. Because as t gets close to 0, t squared is getting close to 0. Add 9 to that, you're getting close to 9. Getting close to the square root of 9, which is 3. And 3 minus 3 in the numerator is getting close to 0. So the whole top is getting close to 0. The bottom is getting close to 0, and so you have a 0 over 0 situation. Okay, as I said, I'm not going to go into detail on this, but here's what the book does. They plug in some numbers for t. They try some numbers like 0.1, and then 0.01, and then 0.001, and they plug those numbers in for t, and then they calculate this quantity, and they see what happens. And just judging from that, you might get a sense of what the limit of this is. You might get a sense of what it is. It'd be like trying to draw a bunch of data points and seeing what the pattern is. I highly recommend that you do that. Now, this is such a wonderful example because it shows you that that kind of analysis is not good enough. In fact, this particular example is really good for more advanced work, and it's good for us to start thinking about it. Just sort of file it away into the back of your head, because it's a nasty, nasty example that unfortunately comes up in the real world a lot, and those of you who are engineers are going to have to know this very, very well. This is an example of something that in numerical analysis is called subtractive cancellation. It always comes up when you have a situation where you're subtracting two numbers together and the answer is approximately 0. And that's what's happening up here in the numerator. You're subtracting two numbers together, the answer is approximately 0, and what you have to file away is that the error in the answer is going to be huge. The percent error is going to be huge. Now, that gets beyond what we need to talk about, but if you look at what the book has written for this particular example, you can see it pretty clearly. The data indicate that the limit of this expression is apparently one number, but it isn't correct. And the book points out and demonstrates from a graph and from other ways that the answer has to be something else. As a matter of fact, not to leave you in suspense, the way to do this problem, and we will later in calculus, the way that we do this problem is by doing something that would horrify high school teachers. You're going to rationalize the numerator. You're going to multiply the top of this and the bottom by square root of t squared plus 9 plus 3, top and bottom. So the numerator gets rationalized and you're unrationalizing the denominator. But you'll be able to tell what's going on after you've done that. Anyway, this problem is a bit more complicated than what we have to talk about at the moment. Okay, so the point of this was to show you that we can talk about change, the change in one quantity with respect to some other quantity, often time, but not always. And when we do that in the idea of getting to the instantaneous rate of change, we're always looking at that denominator quantity as getting smaller and smaller, getting closer and closer to 0. And the limit of this quantity, what happens to that ratio as this guy goes to 0, as the bottom goes to 0, what happens to this ratio? That's what's called the instantaneous rate of change. Okay, there's actually a nice picture of this. Let's look at that. For a graphical image of this whole thing, let's look at the change in going from here to here. Right? So if you start at this point and you go all the way to this point, your distance curve could look, or whatever it is that you're studying, could look like that. So at point A, you might be right there. And at point B, you'd be up here. We were just calculating, and let's say that the quantity that you're, let's use a reasonable variable here, we're going to measure y this way. How unique. So y is going to be measured up and down. So what we are really talking about here is the change in y with respect to a change in x. So x is measured this way. So what's the change in x? Well, that's easy. That would be b minus a. If you calculate this change in x, you went from a to b. How far is that? Well, that's b minus a, the distance from a to b. On the other hand, if you went from this point in space, to this point over here in space, how far have you gone? Well, from the graph you can see that you've gone from here to here. Let's label these points. Let's call this capital P, and let's call this capital Q. So then the change in y, just looking at this picture, is Q minus P, the bigger minus the smaller. So what do you get when you calculate the change in y divided by the change in x? This quantity by itself is the average rate of change. The average rate of change in going from here to there. So that would be Q minus P divided by B minus A. Q minus P divided by B minus A. You've seen this kind of thing before, haven't you? This is exactly what is the slope of a line that connects these 2 points. So if you think about this line that connects these 2 points, the slope of that line is this quantity, Q minus P divided by B minus A. And it would be geometrically this distance divided by that distance. Or you could say rise over run. And you've done this before in calculating equations of lines and things like that. So this rise over run is the slope, and it's also the rate of change in going from here to there. But it's the average rate of change, because we haven't taken a smaller and smaller and smaller time interval. So what happens if you think about this point B now, instead of being a constant, what if you think about it as being a point that can move? So like you call it x now, and x can start scrunching down to A. What happens to this line? Well, you can see this point sort of sliding along the curve and making its way down to A. And each time it moves, you could think of getting a new line that connects the dots. So here you would get another line, here you'd get another line, here you'd get another line. And as you get closer and closer here, these lines are pretty steep, you see. Here, this line was not very steep at all. This line is very steep. So what this corresponds to, let me zoom in on this picture for you. The curve looked like this, right? And if you're starting here and you're moving along this curve, most of you can probably figure out what's happening. You're moving very fast here compared to how fast you're moving up here. You're covering a large distance in a very small period of time, as opposed to a smaller distance, like from here to here, vertically, in a larger period of time. So the rate of change here, your instantaneous rate of change at this point, would be fairly big compared to at other points. If you look at your graph again, you can sort of read this kind of in English. Here, where the curve is going up rapidly, your speed is going up rapidly. Here, where the curve just sort of flattens out, you're not traveling at all. You're not moving forward at all, and your speed would be 0. When you're going this way, you're sort of returning towards Valparaiso. It's like the curve, the road has bent back on itself a little bit, and then you start moving back forward towards your destination. But each time the road is steep like the curve is steep like this, your speed is high. When the curve is not steep, your speed is low. And what you're seeing here, if you zoom in, these lines become closer and closer to a special line that you recognize from way back in geometry when you looked at circles, the special line that is called the tangent line. The tangent line touches the circle at only one point, but that's not the key to understand tangency. To understand tangency, you really have to look at this line as it compares with other lines here. Imagine this line, what happens if you take this point and let it slide around the circle. Can you see what's going to happen? This line, compared to this line, is going to make kind of like a mouth. And the mouth will close as you come around this circle. And if this mouth closes, then you have tangency. this line is a tangent line. As you'll see in other examples, you might have a curve that looks kind of like this. You have what we might call a cusp. And so if you're at this point and you're looking from this side, your lines might get close to something like this, and from this side your lines might get close to that, but the mouth never closes, right? The mouth would look like this, and it doesn't get any closer than that. So the idea of tangency is a little bit complicated. It's not necessarily what you might expect. So here's the idea. The tangent line is this line that grazes the curve, and as you'll see in the lab, this is the real key to it. I don't care what the curve looks like. If you zoom in on any point, and you zoom in, window in on this point, what you will eventually see, if you're zooming in on that point, if you window in and keep windowing in and keep windowing in, what you will see is that the window eventually shows you something that looks straight. Any curve, no matter how curvy it is, if you keep zooming in on it, assuming the curve is at all nice, if you keep zooming in on it, it will eventually straighten out. In other words, locally, if you get in close enough, it will be just like a straight line, and a straight line is something that we can talk about where the average speed from here to here would be exactly the same as the instantaneous speed, because its speed is constant over here. It's not getting faster or slower, it's staying at the same rate. The rise over the run doesn't change when you have a straight line like that. Wait until the lab on Thursday when we zoom in on functions and see this actually happening. Okay, let's step back and look at some notation, because we need to talk about limits and calculate some limits and talk about limits in slightly different ways. So for this example, whatever it is that we were looking at, a few minutes ago we were looking at a t squared minus 1 over t minus 1 and asking the question, what happens to this thing as t gets close to 1? We can write this compactly by using this notation, LIM, which stands for limit, and then we write underneath it t arrow 1. And this notation means the limit as t gets close to 1 of that mess. And in this case it's t squared minus 1 over t minus 1. So in English, that's how we read this. The limit as t approaches 1 of the limit as t approaches or gets close to. Same thing. As t approaches or gets close to 1. So in general, here's how we will write it. It's the limit as, and we could use t, we can use any letter, as x approaches a constant a of some function f of x. So here's what we will say. The limit as x approaches a of some function of x is L. And what that means on a graph is that as x gets closer and closer to a, the value of the function is getting closer and closer to this number, which would be L. Now in this kind of picture, it's pretty obvious that that sort of thing happens. But sometimes it's not at all clear what's going to happen. Give you one more example that we'll look at a lot in the lab and at other times. A very, very important example. What do you think happens to this as x gets close to 0? Sine x over x. In case you've forgotten, the sine function gets close to 0. Here's the graph of the sine. Remember that? The sine gets close to 0 here at the origin. So the top is getting close to 0 as x gets close to 0. The bottom obviously is getting close to 0. So this is one of those nasty 0 over 0 situations where you can't tell what's going on. But you can if you look at the graph of sine x over x. And we'll do that in the lab. All right? So here, I won't keep you in suspense. I'll tell you what the answer is. The answer is 1. And the graph of sine x, so this is just the graph of sine x. So you have to graph the ratio of sine x to x, y equals x. And the graph of that ends up looking like, well, you know, the domain of this has a hole in it at x equal to 0 because you can't plug 0 into this function. And the graph is going to come in like this. But it will get closer and closer. The y values are going to get closer and closer to 1 as x gets closer and closer to 0. All right? Now this is not the homework, not the, the exercises that you're going to be doing in class on Wednesday, but this is what you need to understand, because the exercises that you're going to be doing are kind of stupid. They're examples where you can figure out the answer just by looking at it, just by sort of plugging things in. So for instance, you can ask, what's the limit as x approaches 0 of 2x minus 1? Take a wild guess. As x gets close to 0, 2x is getting close to 0, so 2x minus 1 is getting close to minus 1. No big deal. What's the limit as x approaches 4 of 3x squared minus 16? Just leave it at that. Well, as x gets close to 4, x squared is getting close to 16. 3 times 16 is getting close to 48. 48 minus 16 would be what you'd expect, 32. If I did my arithmetic right. And that's right. So most of the time, these limits are pretty easy to compute. It's only when you get into these problems like what happens if you've got sine x over x as x gets close to 0. What happens if you've got x squared minus 1 over x minus 1. Top and bottom are both going to 0. And then you end up having to do algebra in the easy cases, canceling stuff off, and then being able to figure out what happened. So those are kind of the exercises that you're going to have to end up doing in class. And lastly, we need to look at the notation where we talk about limits coming from one direction or another. A lot of times, the domain of a function only starts at a certain point, like at a point A. So you've got a graph coming like this, and there's nothing on the left side. And so the question is, what happens to this function as x gets closer and closer and closer to A, but only from this side because we don't care about what happens on the other side. Maybe there's nothing in the function on the other side, but we care about what happens as x gets close to A. So we talk about as x gets close to A from the positive direction, and we write a plus like that after the A, almost as an exponent. X approaches A from the positive direction. And so if that's the question, then we talk about the limit as x approaches A from the positive side of f of x. Similarly, we can talk about the limit as x approaches A from the negative side of a function. So we're taking a look there at a number A and a function where we know what the function is doing on the left side of A, not necessarily from the right. Maybe from the right it's doing something totally different. But we ask the question, what's happening as x approaches A from the left? In fact, let's look at this example and make up some numbers. So this point right here, let's say, is equal to a y value of 4. And this value right here is equal to a y value of 2. Then in this case, if this is our function, which sort of proceeds over here and it's getting closer and closer to 4, and on this side we're getting closer and closer to 2, then what we can say in this case is that the limit as x approaches A from the left of this function would be 2. But the limit as x approaches A from the right of this function would be 4. I did that backwards, didn't I? As x approaches A from the left, this is the left. The y values are up here. The y values are up here. And so as x approaches a from the left, the y values are getting close to 4. And as x approaches a from the right, the y values are down here for this function. This function is all f, whether it's from the left or from the right. As x approaches a from the right, the y values are all down here, and they're getting close to 2. Now this is a weird function, but not so unusual. This comes up from one direction, you seem to be ending up at this point. From another direction, you end up at another point. So this comes up so many times that we have to be able to talk about these limits from one side and from the other. And it can happen that they end up being in different places. And so this will be an important observation. In fact, if the limit from the left and the limit from the right are two different numbers, then we say the limit, back up here, where we were just talking about the limit, that limit at a cannot exist. So for the limit at a to exist as a real number, the limit from the left and the limit from the right have to give you the same thing. If they don't give you the same thing, you get different answers, the limit does not exist. Even though the limit from the left exists and it's something, the limit from the right exists and it's something else. Okay, let me summarize that. For the limit, let's do it on a new sheet of paper. This is getting a little too messed up. So, the limit as x approaches a of f of x equal to L. For that limit to exist, for L to be a real number, for this to be true, we must have the limit as x approaches a from the left, from the minus side of f of x, and the limit as x approaches a from the right of f of x. Those two guys have to be the same. If they're not, then the limit does not exist. So you can have a limit from the left, and you can have a limit from the right, and if they're different, this limit does not exist. But the limit from the left is something, and the limit from the right is something else, and that might be useful. All right? One last limit, and that is what happens if the answer is infinite. And here's an example. I love this example. What's the limit as x approaches 0 from the right of the log? Let's say natural log. That's my favorite because it's fewer characters. What happens here as x approaches 0 from the right? Remember, the log function looks like this. It goes through this point 1, 0. But the question is, what's happening as x gets closer and closer to 0? And you can see the y values are going down, 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 down without any limit. They get closer and closer to the y-axis, but they go down here, and they're going off the chart, out of the window. We say that in this case, this function is blowing up, or going to infinity. In fact, we would write it this way. This would be negative infinity. So in this particular case, the limit as x approaches 0 from the positive side, because we're coming in from the positive numbers, is minus infinity. And this is in fact what we mean by a vertical asymptote. A vertical asymptote occurs exactly when you get this infinite limit going on. If you don't have an infinite limit, there is no vertical asymptote. So it's not until we can talk about limits that vertical asymptotes really mean something. So for you to have a vertical asymptote at a point, you must have a limit from one side becoming infinite, like this. It's not so much the idea that the curve never crosses, although it doesn't. It's that the curve becomes arbitrarily large in absolute value, in this case negative and large, as x gets closer and closer to 0. Right? You see the kind of language that I'm using all this time. I don't care so much what happens at a particular point as much as I care about what happens as x gets closer and closer to some number. Let's take a picture, a graph where you've seen this kind of picture before where you have, somebody asked me about this today, where you've got a point here where the curve may end up going like this, and then on the other side it might end up going like this. So what's going on here? Well, you've got a vertical asymptote that's actually vertical this and going off to plus infinity this way and going down to negative infinity that way. So if this is the point A, then you might say that the limit as x approaches A from the negative side, from the minus side, for this function f of x would be, guess what? Plus infinity. Whereas on the other side, when this function is going down on the other side of A, you would say the limit as x approaches A from the positive side of f of x. So x is getting closer and closer to A from the positive side, but the y values are blowing up in the negative direction, so this is again a minus infinity type of situation. Right? So that's the theory, and let's see how well we can do with some particular homework examples or exercises. See you later.